Okay, good morning. Okay, we come to a real business from this class, as we already learned what is maxwell equations. We learned the integral form, we learned the differential form, and we mentioned differential form is much more useful than integral form. For any kind of electromagnetic wave problems, what we really need to deal with is to solve Maxwell equations subject to a given boundary condition. So-called the boundary condition is what problem you are describing, right? For example, you are talking about electromagnetic wave propagation in space, then that is maybe the easiest problem because you couldn't see any other object around you, right? If you talk about how to find the electromagnetic wave distribution inside my office, that is a very challenging problem because I have a furniture, I have a wall, I have a window, and you don't know where this wave coming from, right? And then same as the problem, say, electromagnetic wave propagation down the street in Central. That is also a very complex problem, right? And then for different problems, we are dealing with different boundary conditions, and then the difficulty varies, okay? But no matter what, we have to deal with Maxwell equations. So in this sense, let's start from a simple electromagnetic problem. The problem is electromagnetic wave propagating down an infinitely large free space, all right? So we don't have any other obstacles, okay? Or even we don't see our human body, right? And just let the wave travel. How to describe it, okay, mathematically. We have one question left in assignment 3 is let you to derive the two divergence equations derived from two curl equations, okay? The two curl equations, one is the Faraday's law, one is Am's law, right? So that describe, one is described by the curl of electrical field and equal to the time derivative with magnetic field. Or the Am's law is the curl of magnetic field equal to the time derivative of electrical field, partial d, partial t, right? Okay, then we will start our discussion only from the curl equation. So because curl equation is can fully describe electromagnetic problem. Okay, now let's look at a very simple case. Okay, what simple case is we have electrical field then polarized in x direction. Okay, so that is electrical field polarized in x direction. Also, for now, okay, we assume magnetic field polarized in y direction. Then you may ask me, how do you know the electrical field? When electrical field polarized in x direction, you must have magnetic field in y direction. Okay. At this moment, I have to admit, I don't know. Okay. I just assume there exist. If the Maxwell equations tell us, yes, you can find a solution, okay, for such a scenario that Ex and Hy both exist. If you can find a solution in Maxwell equations, then that means this is possible, right? If you couldn't find a solution, then let's find some other solution. Okay. Let's discuss this case to solve Maxwell equations. Okay. We said let's deal with Faraday's law. Okay. Right, and Ohm's law. Right. So these two equations we need to deal with every day. Okay. Now let's take a close look. Let's take a close look of these two equations again. Okay. The close look of the equation. First equation tells us when the magnetic field changes with time, right? Because partial B, partial T not equal to 0, that means change with time, right? Then you will create electrical field. That electrical field, the curl of the electrical field, will not equal to 0, right? The second equation, Ohm's law, tells you, okay, the magnetic field H generated by two sources. One is time varying electrical field, right? The D is the electrical field flux density. When partial D, partial T not equal to 0, so this is the source. And another very interesting thing is J. What is J? J say, oh, current density. Yes, current density. If I ask you in my office or at your home, where you can see the current, can you see the current J? In space, in room? If you don't see the J, right, can your mobile phone pick up signal? Because your mobile phone pick up electromagnetic waves by the antenna installed on the phone, right? If you don't see the current, but you still can pick up signal, what that means is the field around you, okay, is created by this guy, okay, by the time varying electrical field. So the current J only exists in a very, very small region. For example, you see when your phone transmitting, okay, when your phone transmitting, somewhere in the circuitry in your phone, you create this current. This current may distribute around your antennas, okay? That is a place you have current J. But in any of the, most of the region, okay, where we are interested in knowing the electrical field, we don't have current J, right? We don't have current J. So we have a field point, right? We have a source point. Okay, because now everything we talk about the point, right? Okay, the point means that described by differential equation. When we describe field point and the source point, okay, where we can see very unlikely in the field point there is current J. Okay, you understand? That's not current J, right? So therefore, in our following discussion, we don't consider current J. What we need to consider the current J is that is when we know the source distribution, or maybe this current is flowing on the base station antenna installed on the rooftop, okay? On the rooftop, somewhere you say next building, right? But the field point somewhere is in our office. So that's why we are not interested to involve current J in our discussion, right? Okay. Then let's start our discussion how to find the field solution for the EX, we said EX and HY. Okay, to find the solution for that from Maxwell equations, then let's expand the Maxwell equation. Let's expand the Faraday's law first. Faraday's law, let's look at the left-hand side. Okay, the curl of electrical field. If I write the curl of electrical field, sure, I can remember it, but you don't need to. But that would be nice if you can remember it, right? Okay, this is X component. Okay, how I remember it, the curl is I just remember Y, Z, Z, X, X, Y. So when you know Z, so this must be Z. Okay, so this must be Y. Okay, then X, right, Z. So and so on. So that is the way how I remember it. All right. Okay. Now let's say this is a left-hand side, right? So right-hand side, let's look at that is a time derivativity, right? Then we can write this is like mu 0 h. You see, because I like in the discussion, when we say electrical field, I use E, magnetic field, I use H. So I convert B with H. So because B equal to mu times H. Oh, by the way, yesterday a student asked a question, a very interesting question, how the permeability and the permittivity in free space is determined. Okay, then so I found some interesting material online and then compile them, and I asked TA to post it. So that will be interesting material to read, right? Okay, so what this is we have 3 components, right? No. Okay, so we have 3 components. We have 3 components. Okay, and then one more assumption I like to make is even though the electrical field, okay, the electrical field polarized because electrical field is a vector. We have to get used to vector field. That means you have polarization. That means the component, right? So I like to make another another assumption is once the electrical field and the magnetic field in only two components, right? Then I also assume the field does not change in x direction, does not change in y direction. Okay, so that means these two conditions need to be satisfied. Okay, need to be satisfied. So that means the solution will not be the function of is x and y, but however it polarized in x and y, right? Okay, then in this case, let's look at our curl E, right? Let's look at our curl E. So partial y equal to 0, right? This equal to 0 because partial y equal to 0, right? Then partial x equal to 0, right? So partial x, partial y both equal to 0. So we only have very few components, only few elements left. Okay, only few elements left, right? So only few elements, let's say we have electrical field only exists is x component. That means this term should remain, right? Okay, this term should remain. And then we have, I can see some of our students watch our class and were sleeping in the bed. So that is a very encouraging things, right? So I try to make my class more interesting, okay? So, and put you into sleep. Okay, then how about this term? How about this term? This term also 0, right? Because we don't have y component for electrical field. So this is gone. Okay, when you look at curl of E, right? We only have one component left, which is this. All right. All right. Okay. So this is some component in y component. And look at the right-hand side. The y component on the right-hand side is this guy. All right, this guy. So therefore we have something is partial equal to minus y component partial t. All right. So this is how we got the first equation. How we obtain the first equation. Right. So similarly, you can find okay. Question asks why is this equal to 0? Okay. Question is why is this equal to 0? Because I assume my problem only has EX component exist. Okay, I don't have EY component, of course. EY partial EY partial anything equal to 0. All right. Okay, so good question. Right. So that is the first equation. I gave a detailed derivation, right? Then we have the first equation. Similarly, if you apply the same idea to the second equation, Am's law, okay, you can obtain the second equation. Okay, you can obtain second equation. And then if I ask you, okay, let's say I don't have EX component, I have EY component, okay, then I have HX component. Can you find the solution? Of course you can, right? All right, so let's continue. Okay, let's continue, right? So we have two important equations we derived, okay, for now, right? So still from these two equations, it's still not that clear why I call electromagnetic wave. Okay, I couldn't say the wave. Let's see how we can observe it is a wave, right? And how we can know the wave, the speed of the wave is this, right? Or let's see, the speed of the wave is this, right? Okay. Then for the first equation, let's take a partial z on this and a partial z on this. Okay. Yeah, yes, all right. So equation, some equation I take directivity with respect to z on both sides. So the first equation, this term come to this, right? Become second order equation. Okay, so become second order. And then why take directivity on this side? So I can interchange partial z and partial t, because this is a very well behaved continuous function. So I can swap the directivity. Okay, I can swap directivity. And this term looks very familiar with, because this term we already know the solution. We already know the solution, right? So this solution is we obtained from epsilon, right? From epsilon. So this I substitute this solution. I substitute this solution into this. Okay, so we obtain this equation, right? So I just little bit reorganize it. We have this. This is a differential equation for electrical field only, but second order differential equation. Okay, second order differential equation. This is a very well-known partial differential equation. This is a very well-known partial differential equation with a name is called wave equation. Okay. So any partial differential equation in such a form, it may not be necessarily electrical field or magnetic field. This could be, let's say, acoustic wave. Okay. This also follow this partial differential equation. Okay. This equation is called wave equation. Why it is called wave equation? Why it is called wave equation? Okay, let's move on. Let's move on. Why is this called wave equation? Before we find the solution, let's further simplify this. Let's do a variable replacement. I define another variable I call tau. Tau is basically a length. The dimension is not necessarily is a length. It's the dimension is in a time. Actually, we can say it later on. Okay. So how it defines this variable is the variable z multiplied by a constant. Then how I do is so I multiply this equation I multiply this on both sides, on upstairs and downstairs. Okay. right? So this, I can say this equal to can you say this, right? You see, because this is like okay. So this is top, right? This is top. So why have this variable replacement? I can write this equation into this. This is a more compact form we call wave equation. Okay, the wave equation. You see, because this and this cancel each other, right? Okay, the wave equation. I can write this wave equation further simplified. This equal to this. Okay, if you don't agree, you just apply, do the multiplication, right? So the partial tau times the partial tau and so on, right? Then you can have this. When this equal to 0, when this equal to 0, I use a red color. I think this is more important. Okay, thicker. When this equal to 0, that means if A dot B equal to 0, that means either A equal to 0 or B equal to 0, right? Right? Or both equal to 0, right? Okay, or both equal to 0. So when this equal to 0, then that means the above equation is satisfied. Either this equal to 0 or this equal to 0. So we have plus or minus sign. This equal to 0. All right. So when this equal to 0, when this equal to 0, then I move the second term on the right-hand side. So the plus minus become minus plus. Okay, become minus plus. Okay, so this is something, right? So we have two possibilities. We have two possibilities. One possibility is equal to, I use a minus sign. And another possibility is plus sign, right? So I use minus sign first. Let's use minus sign first. If you look at this differential equation, if you look at this differential equation without any other condition, okay, without any other stabilization, then we can say the solution is very general. Solution is very general. I can say any function like this, any function f, if its argument is t minus tau, all satisfies this equation. All satisfies this equation. You see, because let's verify this, right? So let's look at the right-hand side, okay? Let's look at the right-hand side. The right-hand side, I substitute f as my solution into it. Why take a derivative with time? So I first consider, you say, this like capital T, right? So I have to do the partial f, partial t, then partial t, capital T, partial small t. So this is the chain rule, right? The chain rule in calculus. So we don't repeat this. So the chain rule, we take chain rule, then this derivativity is a partial f, partial capital T, right? Then partial capital T to partial small t. So this is our derivativity, okay? So we have this solution. This is what happened on the right-hand side. And what happened on the left-hand side is also again, right? The same rule. But this time, when we take derivative with respect to tau, we have a minus sign. Okay, we have a minus sign, so we have a minus sign. So this is equal to minus this. Okay, this basically is this. Then you can see that equal left to equal right. Okay, that means the solution is a very general solution. Is I know any function with argument is t minus tau. Similarly, we can justify, okay, for the other equation, why replace this minus sign by plus sign, okay, one plus sign. Then we can justify its solution is always f t plus tau, okay, t plus tau. So we have found a solution, okay, for these wave equations. The general solution is function, any function f with argument t minus tau. But to be more arbitrary, okay, I multiply a constant a, okay. This is even more arbitrary, right? Okay, so this a is really not necessary to add there, but you see, it doesn't hurt. Okay. Then the second equation is also arbitrary function, but not necessarily the same as f, so I use g, but with argument is t plus tau, okay, with argument of t plus tau. Then in this case, I also multiply a constant b. Okay. Now, let's restore what the original tau is. Tau is a constant square root of mu0 times epsilon 0 times z, right? So we substitute this variable, replace the variable back into our equation. Then the tau, okay, replace the tau by our original variable z and the parameters. So this is this equation. So we go step by step, right? We go step by step. Then this is our solution for electrical field. You will say, Professor, what is this? You didn't tell us what is F, what is G. Okay, don't worry. So far, it is a solution. Okay, so far it is a solution because we didn't miss anything, right? We didn't miss anything. Then, since we also know the relationship between electrical field, which is in X component polarized in X direction, and also the magnetic field polarized in in Y direction, HY, right? We know this, they are related by this. Okay, this is from Am's law. Okay, then let's find out what is magnetic field. Okay, what is magnetic field? Magnetic field is, okay, I divide on both sides. I divide mu0 on both sides. Okay, why divide mu0 on both sides? Okay, then let's look at this. Okay, then let's look at this. This is something we need to take a derivative of electrical field with respect to Z, right? With respect to Z. So how we take derivative partial f, which is a function of Z, okay, partial Z, okay. Again, right, this I call capital Z, okay, I call capital Z. So this equal to partial f partial capital Z, then partial capital Z, partial small z, right? Okay, so this is we call prime. Okay, then this partial z, the second term is partial z is a minus multiply this. Okay, multiply by this. So this is a when we multiply by this, don't forget we also divide mu 0, right? We divide mu 0. This divide mu 0. This divide mu 0. Okay, so this is a minus sign derivative. Then this is a mu epsilon mu. Okay, so this is a cancel. Okay, so this is where we get this. Okay, now we know we have this component. Okay, we have this component, and we have a minus sign, but don't forget we have a minus sign here, right? We have minus sign here. So minus sign canceled, right? So this term is partial f or partial f partial capital Z. Okay, right. Similarly, we can get a second term. Okay, so I don't repeat. So then this gives us a very clear picture. What clear picture is? This is a function of partial y partial t, right? Then also I can say this, even though this, I can also say this also equal to partial f partial t. You see, because exactly the same, right? If I take partial f partial t, how I do is partial f partial z, right? Then partial z partial t, and this equal to 1, right? Because this is z. If you take derivative with t equal to 1, right? So that means this is this also derivative with t. This is the derivative with t, this is derivative with t, both with t. So that means if you do the integration over time on both sides, that means I remove the partial t, I remove this guy, I remove this guy, right? This is my solution for magnetic field. This solution is very significant. They have a lot of stories we can read from this. From this solution and this solution. Okay, I repeat here. Okay, I repeat here. Okay, I repeat here, right? So that is a solution of wave equation. That is solution of wave. So it's from these two equations, we can read like people read from your palm, right? They can tell you what's your life, you see, will be about, right? Now let's read palm from these two equations. Okay, these two equations. First, we can say this is a wave equation. Why it is a wave equation? Why I call it is a wave equation? If I look at function f, let's look at the first term. Okay, let's look at the first term. if time increase, time always increase, time never be can be decreased, right? When time increase, in order to keep the function f unchanged, what I should do is this also need to be increased, right? This also need to be increased, right? So when this increase, that means if I call this term, if I call this term as a phase, it's a phase term, phi. So that means phi must be a constant. Okay, when t increase, also should increase, but this is constant. This is constant. This is constant. What I can increase is z, right? So that means z must increase, right? If I rewrite this term, is I write like this. Okay. If I write like this, that means t increase, z increase in order to keep the same speed, right? So this become speed of the wave. Okay, so that means the wave carries the same function value, f, okay, move at speed of Vp, at speed of this, right? You see, distance divided by speed is time, right? How much time is travel depends on how much time you increase. How much time you increase. Now you agree this is this solution is a wave that describes a wave phenomenon. And then this is velocity. Okay, this is the velocity, right? And how about the other term? The other term is a g, right? The g means when time increase, that must decrease. Okay, that must decrease. That means the wave propagates in opposite direction. In opposite direction. So the wave propagates, one is positive z direction, one is in negative z direction. Okay, negative z direction. And this, the wave speed or velocity that exactly equal to the speed of light. Okay, because we know the permittivity in free space. Okay, in free space. So that is the direct. You see, the first two stories. Okay, we can tell from the solutions. Okay, from the solutions. Okay, let's take a break. Okay, let's continue our discussion. Just now we said, okay, from the solutions, we can say this is a wave. That solution describes a wave phenomenon, and two solutions. One for the wave propagate in positive z direction, and another is propagate in minus z direction, okay? Minus z direction, and with the velocity that equal to the speed of light, okay? And also, by the way, by now you convince our original assumption that electrical field in x direction and the magnetic field in y direction, the solution exists, right? So the propagation direction is in that direction, right? The propagation direction. So because this is a function of z only, the propagation direction. But not only we have assumption for these two components, we know the partial y equal to 0, partial x equal to 0. Okay, so those are also a condition to describe this wave. And we also mentioned the t minus, this we can define as a phase. Okay, we define the phase. And this phase only define when z equal to a constant, right? When z equal to constant. That means everywhere in this plane, this phase plane, okay? So we have a wave, we have a phase plane. The wave propagate in this phase plane. This phase plane is a plane. This is propagation direction. So this we call a phase plane. This is the plane, okay? So that's why we gave such a wave, we gave a very illustrative name we call plane wave. Okay, the plane wave. The plane wave is the simplest solution of Maxwell equations, and also is the most useful wave description. Okay, most wave representation among all the possible solutions of Maxwell equations. Okay, very useful and simplest. Of course, we need to learn it very well. Okay, then we can use the plane wave to describe many phenomena. Okay, that engineering useful in engineering problems. Okay, in solving engineering problems, and not only for the electromagnetic wave propagating in space, and also for electromagnetic wave propagating down the circuit, even in ordinary high frequency circuit, and also the wave propagating inside IC, and also the wave propagating inside the fiber optics is also we can represent as a kind of plane wave. Okay, so plane wave is very useful and very important, this plane wave. Okay, I couldn't put more emphasis on this. All right. Let's continue the discussion. If we take say this is propagated in that direction, this also propagates in that direction. One is electric field, one is magnetic field. Okay, if we take the ratio of this EX propagate in positive z direction and HY propagate in positive direction, you better put a plus sign. Okay, the propagating in positive z direction, if you take a ratio of them, this ratio equal to also a constant. This constant we gave a very special name. Usually if something gave a special name, they must have very important position. Okay, so we call the intricate. Sorry, we call intrinsic impedance. Okay, intrinsic impedance. Intrinsic impedance means that is this impedance is determined by the nature of the surrounding material. Okay, so in our case, the surrounding material is a free space. So we have determined by mu zero and epsilon zero. Okay, so this is in intrinsic means. Okay, and this intrinsic impedance is a constant. That constant is about 120 pi. Oh, okay, 120 pi. So this is means in free space when electromagnetic wave propagating, okay, in the medium, what this impedance is. Okay, what this impedance. All right, okay. Okay, anyway, so the last thing is we make a summary, right? And we know electromagnetic field, they propagate like a Planck wave, they are propagating in phase, right? You see the so-called in phase. Just look at this phase term for electrical field and the magnetic field is the same, right? And the ratio of the component of of EX propagate in positive z direction HY, this equal to a real number, right? Real number. This real number. So that means they don't have a phase difference. So that means electrical field and magnetic field, they propagate in phase. And you say, no, it's not the case. Let's compare this. If we compare the wave, propagating in minus that direction, okay? So that means this is plus sign, this is minus sign, right? So this equal to minus 120 pi, right? Yes, so this observation is very correct, but this doesn't mean they're not propagating in phase. This only reflects the fact that if we have X component, Y component, this is propagating the propagation direction. Okay, and later on we will learn. So that follow electrical field cross magnetic field, E cross H. The thumb point to the propagation direction. Or you may interested in my globe. This is my technician bought for me. So it's very special. So why my hand touch my touch screen so that I won't get infected. All right. So this is the case. Okay. Then once the wave propagating in minus Y direction, the magnetic field, oh sorry, this is still the Y axis, but the magnetic field must opposite side, okay, such that still E cross H some point to the propagation direction. Okay, this is propagation. This is propagation direction. Okay, so the electrical field, magnetic field still follow the right-hand rule. Okay, so this minus sign tells you a magnetic field showed opposite sign compared to propagating in positive z direction. All right. So this is the discussion. We found the solution for magnetic field. Okay. All right. Okay. Now let's answer the question. What question is how to determine function f and g? What are they? Okay, what are they? Right. We haven't decided yet, right? But we know you say any function that as long as you have the argument in this form that satisfies the wave equation, right? But we haven't stipulated what kind of a wave yet, right? Okay. Sure, this wave satisfies Maxwell equations. Now let's focus on our problem to a sinusoid time varying field. Sinusoidal means if your signal, if your voltage, say, for example, change in such a fashion, we call sinusoidal wave or sinusoidal signal. Sinusoidal signal, I don't like to repeat how important it is, right? It is say, if you know what is the Fourier series, what is the Fourier transformation, we all deal with sinusoidal wave, right? And then any signal in time, right, we can decompose into infinite number of sinusoidal waves, right? So if we know the solution of sinusoidal wave for one particular frequency omega, then we can find the solution for other omega, then we can compose any time, any kind of response in time, right? So sinusoidal wave also very easy to generate, right? Because it rotates uniformly along the angular directions, right? So that is a sinusoidal wave. Right? Then when we focus on the signal that is change with time sinusoidally, okay, change with time sinusoidally, then we can represent the f in terms of sinusoidal function. Now let's say f is sine or f is cosine. Cosine and sine is the same thing, right? Cosine omega t equal to sine omega t minus pi over 2, right? So it's just a phase shift. It's just a phase shift. So this is a very straightforward, right? This is very straightforward. We convert cosine or sine. Let's look at. Let's use a cosine just as our reference. Okay. Then we need to write f in such a way that time then let's write in this way, right? Let's write in this way. So if we write in this way, we say, oh, we should say omega time, this time must be written like this. Okay, this is in the same form, right? This in the form of ft minus z divided by the speed. Okay. Then also we consider wave traveling in minus z direction, we have a minus. Okay. Then we can say this is omega t minus plus omega divided by v and z. Okay, and z. Then we define these things as beta. Okay, that means omega divided by, this is the speed of phase. Okay, speed of phase, right? So speed of phase, that equal to beta. Beta we give a name, we call wave number. So it is a number. So it is a number. We will have a more discussion on this. So beta is nothing. Beta is omega, right? Beta is omega divided by phase velocity, and what the omega is, right? So omega is angular frequency. Okay, 2 pi f. Then what is this? If I define this, this is what we call constant A, right? So constant A can be anything, right? Can be anything. Then if constant A is this, then constant, we can determine magnetic field is this, because the magnetic field is constant A for electrical field divided by intrinsic wave impedance, eta 0. Okay, eta 0. So which follows this, right? This is magnetic field. So this is a very special case. This is a very special case of the Maxwell equation solutions when the signal change with time sinusoidally. Right? Then this is also the form we will pay most of time to discuss it, right? Then we repeat this solution. Let's have some discussion. Let's have a discussion on this. Then first of all, we define this as our phase. Okay, because this is called the phase of the field. Okay, if the phase, how the phase change with time? How the phase change with time? Then everything, if we like to study how it changes with time, we take directivity with time. So partial phi, partial t, obviously, that equal to omega. Okay, then we know, oh, omega is what? Is a frequency of phase change, right? Frequency of change. What the change, how many cycles per second, right? How many cycles per second? So that is the angular frequency, or this equal to this. If we look at this solution, okay, this solution is polarized in x direction, right? Then I already write this magnitude equal to this, okay, magnitude equal to this. So this propagate, I put plus sign, means wave propagate in positive z direction and polarize in x direction. Remember, we have two vectors. We always need to deal with these two different physical meanings. One is a polarization direction. That means the electrical field is vector, okay? And another is we have a propagation direction. propagation direction, y mean direction, that means it's also a vector, okay? So in this solution, when electrical field polarized in x direction, then the propagation direction is in that direction, okay, in that direction. But propagation direction, we don't reflect here, okay, we don't reflect here. How we reflect the propagation direction is when you give electrical field polarization direction, you also give a magnetic field polarization direction. Then we use right-hand rule, we can determine what is the propagation direction, right? Because E cross H is a propagation direction. Okay, now let's look at this expression. Let's look at this expression. How we observe this? How we observe this? Let's fix our location first. Okay, where we observe this wave, okay, we fix z equal to 0. We fix z equal to 0. So this become cosine omega t, right? Now we draw this with t change, okay? When t equal to 0, this reaches to maximum with magnitude of this, okay? Then how it change is just sinusoidal change, right? Sinusoidal change. When omega t smaller than pi over 2, or t less than 2 omega, right? This is a positive, okay? Then after that is negative, and then positive again and then negative again, right? So this is how the polarization of the wave change, okay? How the polarization. So this is then you can see when we stand in a certain location, if we can watch the wave moving from us, okay, then we can see how the polarization change up and down from maximum to minimum to 0, and then change the direction and then repeat, right? Okay, so let's observe how the phase change with the location, okay? If the phase change the location, we observe how phase change with the location. We take a phase with respect to, take derivative with respect to propagation variable z, okay? Then that equal to beta, okay? That equal to beta. Okay. So don't worry about plus or minus sign. That only indicate where the wave propagate. Okay, what direction this wave propagate. So that means, okay, that means if we take a snapshot at a certain time instant, okay, we take a snapshot at time instant. So that means this term become constant. Okay, this term become constant. Then when we observe how the function change with z, so this is still a sinusoidal function, right? But with different time instance, say if time equal to 0, we take a snapshot, okay, we have this curve, right? This is the time equal to 0. So if you take next time snapshot, when omega t equal to pi over 2, okay, when omega t equal to pi over 2, so this is this curve, right? This is this curve. So that means at different time time snapshot, if you can measure the field along the propagation path, this is a signal strength. You can measure, okay? But this is a mathematical, you can measure. Realistically, it's impossible because this omega is too fast, the frequency. The frequency now we are talking about, say, for Wi-Fi is 2.5 gigahertz. So that means 2.5 times 10 power of 9, okay, per second, okay, per second. So it's too fast. You cannot measure it as time instant. You can measure this wave change, but however, it actually exists, okay, it exists. So this is how we can see the wave, right? And then the phase velocity. What is phase velocity? It means if this phase change, how fast it changes for a given, say, for given time, time duration, how fast it goes, okay, or dz dt, right? Dz dt. We know the omega phase is omega t minus beta times z, okay? So this is phi, right? Then to measure this, then we take derivativity with both delta z and delta t and divide them, okay? Then we can find this phase velocity equal to omega divided by beta, okay, divided by beta. Right, you see, so if we take a derivativity with time, we get omega. We take a derivativity with z, we get beta. So then we divide them. And also, if we multiply the omega, the beta divided by omega divided by beta, right? Then we know this is wavelength, this is frequency, this is frequency. Okay, in another word, from this, we have come up a very useful relation is omega equal to 2 pi divided by lambda. Okay, one question. Okay, so the question is, we are talking about EX, okay? This E equal to EX and polarized in X component, right? Okay, we only have X component. So the question is, where is the EX point upward? The EX will be point to the upward or downward. It depends on at what time. Okay, we said if you fix, look at this. If you fix a location where you observe, right? Say, let's just pick arbitrary, okay? We pick at this point. This is my observation point. This is my eyes, okay? Okay, this is my eyes. I observe the field at this location. Then 1t equal to 0. This is positive. That means point upward, right? Then once the t equal to when omega t equal to pi or t equal to pi divided by pi, this is completely downward. Okay, and also it's a magnitude, not a constant, right? You see, at this time instant, the magnitude equal to 0, right? So the magnitude change, okay, increase to maximum, then decrease to 0, then downward, then decrease to minus minimum, right? And then backward. So that change with time, all right? I hope I answered the question. Did I answer your question? Okay, then so from this relation, we can find the beta is a very useful information. Okay, the beta basically, if you know the wavelength, you know beta. Okay, but this beta also depends on what kind of wavelength, and then I better put G subscription, and to indicate this beta is not, okay, it's not in free space, because in free space, the F and G, F frequency and the wavelength, they are related. Okay, so we discuss this when we discuss specific examples. Okay, now we have to consider our real world. What our real world is? Okay, our real world is our signal we never deal with signal with a single frequency or a single tone. Okay, single tone signal single tone signal is usually useless. It's really useless. You see, because if you only hear a single tone, what does that mean? What does that mean? You just hear a noise. Okay, that noise, you will get bored, right? You will get bored. Now people send the signal with single tone. If you really send a single tone, only information you carry is you're telling people you're still alive. That's it. Okay, no more, right? So we always talk about broadband. That means the wider the bandwidth, the more information you carry, right? And even the Morse code, okay, you have a certain bandwidth. Okay, so let's talk about if we have a two frequency, two tones signal transmit by plane wave, what will happen? Okay, now let's assume we have, this is our frequency, we have omega 0, we have a very narrow band signal. This narrow band signal is, we have, okay, we have a bandwidth we have 2 times delta omega. Okay, so we have two tones. We have two tones. We send the signal plane wave by the two tones to see what is the total signal looks like. Okay, now we have first signal. This is F2, F1. Okay, if this is F2. Then when the frequency increase, the beta also increase accordingly, right? You see, because beta is related to the frequency, okay, related to the wavelength. Then this is the first signal, signal 1. And then this is signal 2. Okay, this is signal 2. And modulated by a little bit less, you see, lower frequency, okay? Lower frequency and also lower beta, okay? So this is second signal. Then if you use a simple trigonometry manipulation, what that means is if a cosine A plus B, you know what that is, right? Cosine A cosine B minus sine A sine B. Okay, you use simple trigonometry function, then this equal to this. Okay, equal to this. What that equal to is we have one signal component. This signal component change with time very fast because this is omega 0. Omega 0 in the order, say, 2.5 gigahertz. Okay, very high. And the third omega may be in kilohertz. Okay, very, very slow. Okay, because this is a very narrow band. Okay, so therefore, this is a signal that change with time very slowly. Change with time very slowly. This signal change with time very fast. So as a result, this is the wave that looks like. Okay, this is a fast change. Fast change wave, right? And this envelope is a slow change wave. Okay, where your information is carried, your information is carried by slow wave, not by fast wave. Okay, so that basically your envelope, we call this is envelope, right? This envelope carry the message, and what really the signal, the speed, is depend on how fast this envelope travel, not how fast this phase change. Okay, this is a very important conclusion. Okay, then if we set this phase, okay, this is we call carrier. The carrier wave. Okay, carrier wave. If we set the phase of the carrier wave constant, then we can find A is phase velocity. Okay, is phase velocity is the phase velocity is a constant that depends on omega 0 and beta 0. Okay, and then this is possible. The phase velocity is a lot larger than the velocity of light. Okay, but however, I said what we're interested in is we call the group velocity. Okay, this group velocity is defined by the envelope. Okay, how fast this envelope goes. Okay, this envelope goes, that means that determined by this phase equal to constant. Okay, when this phase equals constant, that means this point is moving. Okay, this point is moving to here. How long it takes? Okay, how long it takes, right? Then again, we need to find dz dt, right? That measure the phase velocity of group phase velocity, and according to this mathematical solution, that equal to this divided by this or this, right? And once the delta omega approach to 0, okay, this equal to this, okay, 1 over d beta divided by d omega. So this, you can see this is this velocity is never can higher than the speed of light. Let's give one example, okay? Let's give one example. Right now, you look this as very strange expression. I said, okay, in certain media, when electromagnetic wave propagate, its propagation constant or propagation or the wave number, the beta, sometimes called wave number or propagation constant. Okay, so it's something, okay. Also called propagation constant. So the propagation constant for plane wave propagation, it's really possible that beta can be represented by this. Okay, so this is the square root. So this is a function f, and fp is we call kind of cutoff frequency. Okay, then we can represent by this in terms of this is a speed of light. Okay, then in this case, if we look at the phase velocity, okay, according to the discussion we had, that equal to omega divided by beta, then you can see the phase velocity can be larger than speed of light because this number is smaller than 1, right? This number is smaller than 1. But however, if you calculate the group velocity, okay, then you have to take derivative of beta with respect to frequency, omega, okay? But you see, it takes less than a minute, you can find the group velocity, represented by this is always less than speed of light. Okay, always less than speed of light. So this is the way we look at the plane waves. Okay, we look at how fast it propagates, either by in terms of phase or in terms of a group phase, right? One is the velocity of a phase, which is an artificial number, okay? Even though it doesn't, even though it is faster than speed of light, but it doesn't physically realizable, okay? And we pay more attention to the actual signal speed that we call group velocity, right? And sometimes you see we can read the information about the speed, about the wave number or propagation constant, and about you see the magnitude or frequency of the wave from mathematical expressions. Okay, and we have this example, and it's very straightforward for us to read. So I just leave it to you. All right. So I shall leave it to you. And the last things I take just less than 1 minute is at the end of this example, we can plot the field. We can plot the field, the electrical field. Okay, this is electrical field. Okay, the magnetic field. Okay, so both electrical field and the magnetic field. Okay, this absolute scale is not comparable. Okay, it's this drawing is not in scale. Okay, not in scale. But one thing you can say is, first, the electrical field, if we say polarized in x direction, doesn't mean always pointing to upward or downward, because it changes with time. It changes with time, right? And the magnetic field also changes with time, right? Changes with time. But however, it's always in phase. You see, because when electrical field reaches to maximum, magnetic field reaches to maximum. When electrical field reaches to zero, magnetic field reaches to zero, right? When electrical field changes sign, magnetic field changes. So this is so-called in phase. Okay, so so-called in phase, and always follow right-hand rule. Okay, always follow right-hand rule, right? E cross H. Right, always follow right-hand rule. And when electrical field points downward, and the magnetic field also changes direction, also still follow right-hand rule. Okay, still follow right. And that example, I just leave it to you as homework. Okay, so that is additional homework for you to read. And in homework, I gave every time each homework, I try to limit to four problems. Okay, so this is additional problems. Okay, that is what I want to discuss today. I should say, plane wave is most important concept in this class. Okay, this is the first class and the most important class. I won't, you see, the things we have discussed, I won't come back to repeat this again. If you couldn't understand well, you are very easily to get lost, okay, in rest of discussion. And if you ask, you say, for the problem of in final exam, in middle term exam, I should say maybe 80% related to plane wave, all right? And if you couldn't understand it, you must pay more time on it, okay? That's all for today.